This is contribution of conduction. As you see here, there is K here, contribution of conduction. This one, it is, you see here, this is contribution of convection. This one, it is shown by K sub C. This one, it is shown by K sub H. If the element is insulated from the outside, then it is 0. So let's look at this example. And then F here, we looked at this one. So F, these shape functions, if you put them, simple integration of this one, it is given by this. F sub lowercase q, this is conduction from the surface, it is given by this, and convection is this one. So time to look at an example problem. I think we briefly looked at this one, but now let's look at this in more detail. This is a composite wall. 3 materials are here with 3 conductivities. For element 1, it is 5 watts per meter degree centigrade. Element 2, it is 10. Element 3, it is 15. This one. The left end is at 100 degrees centigrade. Right side is at 500 degrees centigrade. And this is the cross section of this, by the way. This is a round, area is 0.1 meters squared, and it is insulated. When it is insulated, there is no convection from this surface. These are the items given. Our model, we have 3 elements. We have 4 nodes. We need to find the stiffness matrix for each of these elements, like what we did in solid mechanics. K is given by this for one-dimensional problems. So we need to apply it to each of these elements. For this problem, this term would be 0. Why? Can somebody tell me why it is 0 for this problem?
Because it's insulated, so that there's not going to be any convection.
Very good, you're right. This is insulated, this is, as you see, insulated, so there is no convection taking place from the surface. So this term would be 0. And we just need to apply this one for each of these elements and create the global stiffness matrix, and then set up the system of equations and solve. For element 1, it is this, AK over L, 1 minus 1 minus 1, 1. This is area, K, length of the element. So this is for element 1, do the same for element 2, it is here. This is for element 3, it is here. Our global stiffness matrix, somebody tell me, what would be the size of the global stiffness matrix? Anyone?
Six by 6.
Why 6 by 6?
Oh wait, no, there's 4 nodes, so 8 by 8.
How? There are 4 nodes, you are right, there are 4 nodes. But how many degrees of freedom per node? Anyone?
It's
How
just
many
1 degree of
degrees
freedom per node.
Isn't it just one?
Wouldn't it be a 4x4?
You're right. This would be 4 by 4 because there is 1 degree of freedom per node. That's temperature. Temperature at this node, it is just temperature. It doesn't have in the X direction or in the Y direction, like what we had displacement, for example, in solid mechanics for 2-dimensional problems, of course. But it's just temperature is temperature, 1 scalar at 1 point, it is 1 unknown. So 4 nodes and 1 degree of freedom per node. So our global stiffness matrix should be 4 by 4. That's it. This is this one. We found K for each element, so put them for element 1, it is here, element 2, element 3. This is our global stiffness matrix multiplied by temperature vector is equal to heat flow vector. This is the system of equations. Time to apply boundary conditions. For this problem, what boundary conditions do we have? Anyone? What are the boundary conditions in this problem?
The
Question.
temperature at either end.
Yes, temperature at this end, it is 100, and at this node, temperature at node 1, it is 100, and at node 4, it is 500. So these are the degrees of freedom we need to, the boundary conditions we need to apply here. So, which means we have to correct this here. We have to correct this first row so that it gives T1 is 100, because T1 is 100. We have to correct this. How do we correct this? We make it 0, make this one 1. I have shown it in red, the changes that you see. So this one, we change it to 0. This one, we change it to 1. And this one, F1 would be 100. That is the boundary condition. If you multiply now this row by this column, it gives T1 is equal to 100. That's what we want. And the same thing for this one, T4. T4 here, we have to change this so that it gives T4 is 500. So do the same, make this term 0 and this term 1. So it gives T4 500. Now, these are intermediate nodes, T2 and T3. These are, you see here, these are intermediate nodes. There is nothing happening here, so they are 0. It's like in solid mechanics, there are no external forces at those two nodes, so they are 0. That's it. This is the system of equations. These are non-homogeneous boundary conditions, by the way. If, let's say in solid mechanics, if displacement were 0, they were homogeneous boundary conditions. But these are non-homogeneous. This is the temperature distribution. That's what we wanted to solve. All right. Any questions about this problem before leaving this document? All right, no question. Let me show you this equation one more time before leaving here. This equation is important. We are going to apply this one later for 2D also. But let's first look at this term, one item here. So this term, let's see what happens. Sometimes from the tip of this last element, you see here in this example problem that we solved, sometimes from the tip of this last element here, from the tip, there is also convection taking place. So we don't have this fixed temperature here, but we have convection taking place from here. So let's see what happens to this term, element stiffness matrix. If there is convection taking place from the tip of the last element, what happens? And what happens also to this one? This takes care of convection. If there is convection taking place, what happens to this term here for that last element? So with this one, let's go and look at our last document. This is the modules, go to this. This is the last document that we are going to discuss. So this is when we have convection taking place from the tip of the last element, like what you see here. Well, it has some effect to K. Remember, I showed you K for contribution of convection, it is given by this, Hn transpose NDS, this. Let's see what happens to this element, node 1, node 2. So for this one, if convection is taking place from this end, the shape function, it would be 0 and 1, because the value of this shape function would be 1 at its own node, and it is 0 at the other node here. So we are evaluating it at the tip of this, and ds integral over this surface, so that would be area. So this is this term. If convection takes place from the tip of the last element at this to K, for that element, for that end, if there is convection taking place from this end, add it to the element stiffness matrix for that element. Now, it has some contribution to F also, with flow vector. heat flow vector, it is given by this H T infinity N transpose ds. This is the formula I showed you, that general, very important formula. It comes from here. The root of everything is back to that equation to begin anyway. So this one applied to this element when there is convection from the tip here, that would be what HT infinity. Shape function would be 0 at this node, and if we evaluate it here, it would be 1 at this node, ds, so that would be area. This is this term added to F if there is convection from the end for that element. All right, that's all. So add this one to K, this one to F, if convection from the last element. All right, that's all I wanted to discuss before looking at an example problem. Any questions before looking at this example problem? All right, now this example problem is the same actually as like what we did. I want to look at two example problems with you. This problem this is a fin. It's a pin fin. Question for you. What is the purpose of a fin in heat transfer? What is the purpose of using a fin? What is a fin?
To increase heat transfer.
How do we increase heat transfer?
You increase the surface area of the surfaces that are in contact with the convection fluid to get rid of more heat.
Very good. Extended surfaces. So these fins are actually extended surfaces. We are extending heat so we can remove heat. That's what we do in electronic cooling, especially. It is very important. And computers, again, thanks to finite element methods, they helped a lot. And these computers are now much more efficient compared to computers 20, 30 years ago. If you look at them, they had problems, serious problems with their heat transfer. But now fins are much more effective, finite element methods helped a lot in modeling. Before making them, we can analyze them, make sure that this is the best design, and then use those designs. So let's solve this problem. This is a fin problem, pin fin. The cross section is round, 100 millimeter long and 4 millimeter round. Temperature at the base is 120 degrees centigrade. Ambient temperature is 25 degrees. The question is, this is a pin fin. Has a circular cross section. The temperature at the base is 120 degrees centigrade. This is here. Temperature of the ambient is 25 degrees centigrade. So this is this one. Conductivity is 168. A material is aluminum. So it has a conductivity of 168 K. Watts meter Kelvin. The convection heat transfer coefficient, it is also given 30. Fins are 100 millimeter long, diameter is 4. Determine the temperature distribution along the fin. Using 5 equally spaced elements. We want to use 5 elements divided into 5 equal length elements. We want to find the temperature distribution, and at the end also we want to find the heat loss for 100 fins. You have 100 of them. You want to see how much heat we remove. All right, to model this is our model. 6 nodes for 5 elements. We need to create the global stiffness matrix. What is the size of the global stiffness matrix here in this problem? Anyone?
Would it be 5 by 5?
Why 5 by 5?
Wouldn't it be 6 by 6 because there's 6 nodes with 1 degree of freedom per node?
Oh, I missed the 6th node. I'm sorry.
All right, very good. Yes, you're right. This is 6. There are 6 nodes and 1 degree of freedom per node. So our global stiffness matrix should be 6 by 6. Each element, there is conduction taking place through the aluminum material, and there is also convection taking place by removing heat over this element from here. It's like surface traction, like surface forces. Heat will be removed from the surface. So each element, conduction and convection. So we need to find K for each of these elements. So let's do this one. K is given by this formula. AK over L this and HPL over 6 this. If you look at this, it is the same for all of these elements. There are 5 elements, so this would be the same for all of them. Area is the same, K is the same, length is the same, perimeter is the same, so H is the same. So everything is the same. Just plug the values. K, the cross-sectional area is pi over 4 diameter squared. This is the cross-section here. Pi over 4d squared. This is area. K is given 168. Length, H is given 30. Perimeter is pi d. Perimeter of this is where this traction or surface is used for convection. Pi times d, length is this one. So adding them, we get this one. This is the same for all of these elements. F is given by this. The only thing here is convection. The formula is this. And if you see here, HTPL, so it is the same for all of these elements. So all these 5 elements, we have the same thing. This is H, perimeter is this one, length is this one, temperature is 25. So this is this one. Set up the system of equation. It is like this. For element 1 sits here, element 2 sits here, element 4 and element 5 times temperature vector is equal to heat flow vector. These are now, you see, F is now this F. This F comes here. For element 1 sits here, for element 2 sits here, so it doubles this one, and then for the end elements, it is just this term, 0.094248, this one, for the end nodes. That's it. Time to apply boundary conditions. Boundary conditions, we have to change it such that T1 is, remember, T1, temperature at node 1, it is 120 degrees centigrade. So we have to change it such that it gives T1 120. So make it 0, make this one 1, and make this one 120. So if you multiply this row by this column, it gives T1, it's 120. That's what we want. That's it, solve it. This is what we get. This is temperature distribution. At the beginning, you see that the temperature drops suddenly, quickly, 120, then it drops to 100, then 87, then 78, 73, 72 slows down. But temperature drop is very high here. So that's what, for this fin, you see temperature drops very quickly here, and then slows down as we move toward the end of this fin. That is the temperature distribution. That's the main task. Now the post-processing. We want to find the heat loss for 100 fins. We need to find it for each fin. But for each fin, you see, since temperatures are different, since these temperatures are different, along this fin. So each of these elements has a different heat loss. Heat that will be dissipated, will be removed, is different for each element. So heat that will be lost for each element is given by this. This is Q for this each element. It is HPL, average temperature minus fluid temperature. Just apply it to each element that you want. We need to find, for example, for element 1, H is 30, perimeter pi times diameter, length Ti, Tj, this is for node, element 1 goes from node 1 to 2, so this is node 1, node 2, T fluid is this. So this is the heat loss for element 1. Do the same thing for element 2, but pay attention for element 2, it would be, this would be T2, T3. If we do this, we get this heat loss. So as you see, element 1 has this heat loss, element 2 has this much heat loss. Do the same thing for other elements 3, 4, 5, adding them together. This is the heat loss for one fin, which consists of 5 elements. 2.34 watts is the heat loss for one fin. We have 100 of them, so multiplied by 100 fin, it gives the total heat loss for an array of 100 fins, which is 234 watts. All right, that was the problem, this problem. Any questions about this problem?
Yeah, I have a question about using the finding the K matrices and the F matrices.
Okay.
You have them as like K1 is equal to K2 is equal to K5, but
Right.
aren't there 6 nodes?
Oh, these are for each element.
Oh, for each
Okay.
element, right. Okay.
This is for each element, not for each node. So this is the element stiffness matrix. That's what we call it, element stiffness matrix. That's for
Right.
each element, not for the nodes. All right. A good question. Any other questions? Anything else? No questions. So let me see. This is this one. I have another example problem. I quickly look at this with you, but I don't want to spend too much time. I prefer to move on to, oh, I have another one also from the textbook. So let me quickly, I have 2 problems before talking about 2-dimensional. So I want to review it very quickly with you. This problem is familiar to you. Remember the house problem, 70 degrees Fahrenheit in the room, 15 degrees the attic, insulation, and also gypsum board. We wanted to find the temperature through the ceiling. So we wanted to find the temperature here, then we wanted to find the temperature here at this end, then here. Then here, of course, we know 70, but we don't know the temperature here and here and here, and then here we know it's 15. So we can solve this problem. Previously we solved this problem using how many? We have 1, 2, 3. We solved this problem using 4 elements. Now we solve the same problem, but using just 2 elements. Why? Well, because it is just convection is taking place to the attic, and convection is taking place from the room here to this ceiling. So we can use just 2 elements and model them as just convection taking place from the temperature inside the room to this. This is the gypsum board, and this is the insulation. This here, this is this insulation here. This is this insulation here, then this is gypsum board. So there is convection taking place here and here. So we can model this and solve this problem by just using 2 elements. That's what you see. connectivity table, just 2 elements are used. So we have the U factors for just element 1 and element 2. By doing this, our K in general is given by this. This is due to conduction, this is due to convection, this is due to the tip of this. Here, this term, we don't have convection from the surrounding walls. Then this would be K1 for element 1. If you apply this one, remember we talked about when we have, today we talked about this. Convection taking place from the end. That's what we are using here. We said that we have to add it to that element, to K, and we have to add this one to F. That's what we are doing here. This one is 0, so this term here is for the tip of this element. It is actually giving this one. This is for the tip of that element. Plug the values here. That would be K. For element 2, again, we have also this for element 2 here. See here, element 2. This is taking place from the tip of this. So for element 2, the same thing. K is given by this because of the tip of this element. Plug the values, this is K. For F, the same thing with flow vector. This would be this one because there is convection from the tip of this, and that gives K F for element 1. For element 2, the same situation. This is 1 and 0, this is 0 and 1. Plug the values, we get this one. This is this one because in this case, we have it at node, this is for element 1. So this is taking place at node 1. For this one, it is at node, this is for element 2. Element 2 goes from node 2 to 3, so it would be for node 3 here. That's what this node 3 here. Convection taking place here. So plug the values. This is our element stiffness, global stiffness matrix. 3 nodes, 3 unknowns, and this is our heat flow vector. These are these terms, this and this for element 1, and for element 2, this one. We have already incorporated the boundary condition. You see, these are already boundary conditions that we used convective type elements. So it's already included here. Solving them is the temperature distribution. The same as what we did before. So this problem we solved it again, but in a different way. Previously we used 4 elements. Now we use 2 elements with convection taking place from the tip of these 2 elements. All right, this is this problem. Any questions about this problem? All right, still I have another problem here. Let me quickly look at this before moving on to talk about heat transfer, 2-dimensional heat transfer problems. This one, this is along the length of a rod. So this is a rod insulated. Examples that's in one of our textbooks. I'll review it quickly with you. We know everything about this. I just let me look at it quickly. It's insulated, 40 inches long. This is the cross section, 1 inch radius. Insulation means there is no convection taking place from this surface. This node is at 100 degrees Fahrenheit. This is convection is taking place from the tip of this element, whatever it is. Everything is given. The temperature is 100 degrees here. Temperature is 10 degrees. Ambient temperature is this. H is given here. K is 20 for this rod. the question is to use 4 elements, as what you see here, 4 elements. So let's divide it into 4 equal length elements. Total length was 40, so this is 10 inches each. Element 1, 2, 3, 4, and 5 nodes. Very similar to what we did, except just for this one, it is convection is taking place from the tip of this last element. The fin problem that we solved, actually, convection was taking place here. For this one, it's just convection taking from the tip of this. So, question for you: what is the size of the global stiffness matrix in this problem?
5 by 5?
5 by 5. 5 nodes and 1 degree of freedom per node. It would be 5 by 5. Find K for each element. This would be this one, K over L, this plus HPL over 6 plus for the end. But element 1 doesn't. This is the general formula, K, incorporating even the end. So for element 1, there is no, this term is 0. Why is this 0 for element 1? Anyone? This term is 0. Why?
There's no convection heat transfer?
Yes, it's insulated. You're right. It is insulated, so there is no convection here. This one, it is also 0. There is no convection taking place here. It's just fixed temperature. So convection is not. So for element 1, it is 0. This is 0. This is just this term. Just plug the values here. This is the same for elements 2 and 3 also. So elements 2 and 3 are the same as this one. Not for element 4. Element 4, convection takes place here. So for this one, for element 4, we need to add this last term. Plug the values. This is for element 4. Heat flow vector, F. For elements 1, 2, and 3, it is 0. There isn't anything happening. There is no Q. There is no conduction taking place. There is no convection taking place. So everything is 0 except for element 4, the tip, convection taking place. And today we looked at this. We said that if this is the case, remember at the beginning for F, include this one. So we need HT infinity A0, 1, 2, for that element 4. That is here. This is for element 4. This is this term. Plug the values. It is here. Apply the boundary conditions. This is the system of equations. 5 equations, 5 unknowns. The only thing here, node 1, temperature, we know temperature is 100. So we have to correct this equation 1 such that it gives T1 is 100. To do this one, you just multiply. I have highlighted this one. Make this one 0 and change this one to 1. That would be 100 here. So if you multiply this row by this column, you get 100. This system is now ready for passing on to Nastran for solution for temperatures, and these are the temperatures: T2, T3, T4, and T5. All right, that was the discussion about this problem. Any questions before moving on and talk about two-dimensional heat transfer problems? All right, no questions. So let's look at the last discussion. two-dimensional heat transfer problems. Remember, the type of element that we used in solid mechanics 2D, it was triangular elements. Triangular element is what you showed here, node I, node J, node M. This is this element. We used it in solid mechanics. This has coordinates x, I, y, I. This one, x, j, y, j, x, m, y, m. Temperature at this node, it is Ti. At this node, it is Tj. At this node, it is Tm. Remember, labeling, it is counterclockwise. Always call it IJM. This is element IJM. So we want to see what heat transfer problems in 2D, how we use finite element methods in this. We did it in solid mechanics. For these triangular elements, the same everything, temperature, very similar, everything analogous to what we did before. Heat transfer, that's what in finite element method, you see most of the books, everything, most of the coverage is in solid mechanics because heat transfer is very analogous to actually solid mechanics solutions. In solid mechanics, we said that very similar to this one, that for example, here we have temperature is given by Ni, Nj, Nm, Ti, Tj, Tm. These are nodal temperatures. This is the temperature, our approximation function, or our interpolation function, sometimes it's called. In solid mechanics, we use displacement functions. Actually, displacement was given by they were shape functions Ni0, Nj0, Nm0, and these were displaced. These were displacement Ui, Vi, Uj, Vj, Um, Vm. These are 2 degree of freedom per node in solid mechanics we had. And this, it was also our shape functions like this. So we found our shape functions in solid mechanics, Ni, Nj, Nm, in terms of all these alphas, betas, and gammas. These are shape functions, and alphas, betas, and gammas, they are given by this function. These are all coordinates of these nodes. And 2a this is twice the area of this element. It is alpha I plus alpha j plus alpha n. So this is for this element. Everything here is the same as what we had in solid mechanics. Now, our goal is always to find the element stiffness matrix. We go back to that general formula. Remember, we said this is K. In heat transfer problem, this is the element stiffness matrix. It has 2 pieces. K sub C, K sub H. K sub C is contribution of conduction. K sub H is contribution of convection. Now, let's see what happens to these terms for this triangular element. To do this one, we need this B. Let's see what is this B. B, remember before when we talked about one-dimensional, we said we defined this. G is temperature gradient. It is dt over dx. In 2D, it is dt over dx, dt over dy. This is temperature gradient. It is B times T. This B for triangular elements is given by this. These are betas and gammas. Our D, this material properties go here. This conduction in the x direction, conduction in the y direction. So this is our D goes here. So this is B and this is D. K sub C. Now this piece, just plug the values. This is B transpose This is D, this is B, this is this B here, multiplying, and these are all what? They are not functions of X and Y. These are just coordinates of these nodes. These are just some numbers. Everything comes out. So K sub C is actually TA B transpose DB. K sub C this is thickness of the element. You see, this is dV. Integrating dV over volume, it is simply thickness of this element. This is the thickness of this triangular element times area of this gives the total volume of this. This is this one times B transpose dB. Everything comes out of this integral. This is our K sub C. This is this piece. All right, so let's look at what happens to this one. This one, K sub H. K sub H is given by this. This is this one, H and transpose NDS. These are shape functions, Ni, Nj, Nm. Multiplying these two matrices, we get this one. We need to integrate over the surface where convection is taking place, but it depends on which side. So K sub H needs to be evaluated for the side with convection. We can move forward with this unless we apply it to a case. So let's look at this example problem. We want to find K sub H for this side ij. So this element has node ijm. This is this triangular element. Length L, convection is taking place from this side ij. So let's see what happens to this equation for that side. For this one, Ni is given by this. This is the formula. 1 over alpha I plus alpha j plus alpha and this. Now for this side, y is what? For side ij, y is what?
0.
0. Y is 0 for this. So this term would be 0 if you find alpha j alpha, and you see that they will be 0. And if we find alpha I here and simplify, we get 1 minus x over L. Usually in the class, I would ask students to do this. We were more sometimes active in the class, of course. So I want you to verify these items. This is for Ni. Nj is given by this formula. This is 1 over 2a is the same as this one, Lm, Lym. For this Nj, this would be 0, y is 0 here. So it would be x over, and m would be 0. So if this is the case, this is Ni, Nj, Nm. Plug it back into Ni, Nj, Nm here. This is Ni, Ni. So this is Ni is this. So this would be this to power 2, and this one. This would be our K sub H. We have to integrate from 0 to L. We can simply integrate this one. We get this one. So this is our K sub H for triangular elements if side ij, convection is taking place from side ij, like in this example. All right, this is about K. This was about K. Now we need to see what's happening for force vector for this. Force vector is here. Heat flow vector or force vector again in solid mechanics. It is given by this. Let's apply to this triangular element. F sub q is given by this. This is what the formula that we looked at today. N transpose q dv. dv, it is thickness. Thickness is constant times area of this element. Now, we need to, this is the shape function, we need to use the shape functions here. I have put a note here that this Q is heat source, internal heat source. It is constant over this element. It is like weight density. If you want to include weight of a structure, the same here, this is heat flow vector Q for this element. It is constant. So this comes out. That's what you see here. dV is thickness times dA. This is shape function. It is easier, integration is simplified if origin of the coordinate is chosen at the centroid of the element. So we need to integrate this, but it's a little bit problematic, you see, because this n shape function, these are functions of x and y here. This is what you see, there are x and y here, and then integration of this over the element, it is a little bit problematic, unless it is much easier if you put this coordinate at the centroid. If you put this at the centroid, these integrals are already 0. And then it is much easier, you can integrate this to get this one, QAT over 3111. AT is what? Is volume. Is area times thickness. Area of this element times its thickness is volume. This is heat per unit volume. Times volume, it is heat. 1/3 goes to each of these nodes. That's what, like in solid mechanics, we wanted to include weight. We said that weight of the element divided into between these three nodes. Now, f sub lowercase q is this one. It is given by this, very similar to this one. So it's the same, actually replacing this with heat flux here per area. So result of this would be this one, but it depends again along what side. It is alongside ij, then it use this one alongside jm. It is given by this, and alongside in, it is given by this. This is for f sub q. F sub h, this one, this is convection. It is very similar to this one. Compare this equation to this one, you see. What? It is n transpose q ds, n transpose, instead of q is ht infinity ds. So it is actually the same as this one. This is constant. This is also a constant. So just whatever we got here, just replace q star here with ht infinity. Q star is assumed constant here. As you see, this is constant. So to do this one, just replace these things. I have put this note here. In these equations, replace f sub q, replace this q star with ht infinity, and that's what you get f sub h. All right, so we looked at everything. We have our heat flow vector f, and we have our k sub c we discussed, and k sub h. We have all the components, and we are ready to solve triangular elements. Any questions before looking at this example problem? All right, no questions. So let's look at this example problem again from our textbook. Since we do it by hand, so let's make a coarse mesh here. This is the problem. It is a two-dimensional body, 2 feet by 2 feet, and thickness is 1 feet, so it has a 1 foot thickness. Insulated here, insulated, temperature at this end 100 degrees Fahrenheit. Here there is convection taking place. H is given 20, temperature of infinity is 50 degrees Fahrenheit. The question is determine the temperature distribution. So for this body, for this, we want to find the temperature distribution. And everything, again, here it is 100 degrees Fahrenheit. We are setting it, fixing it here, and here we have convection taking place. And we know K is given, Kx and Ky, it is 25. So the same conduction heat transfer coefficient is the same in the X direction and in the Y direction. So do this one, this node 1, 2, 3, 4, and 5 here. So we break it down into, we discretize it into 4 elements. Remember, label this counterclockwise. So node element 1, node 1, 2, 5. Element 2, for example, it is 1, 5, 4. Go counterclockwise. Element 3, it is 4, 5, 3. And element 4, it is 2, 3, 5, for example, counterclockwise. So with this one, we need to find element stiffness matrix K. We need these betas for element 1. These are betas and gammas. These are coordinates of these nodes. We did it before. That gives K1 is TAB transpose DB. This is this one, K sub C. We did it here, K sub C. Remember, K consists of 2 pieces, K sub C. It is this one, TAB transpose DB. Apply it to element 1. This for element 1. The TAB transpose DB. This is B transpose DB. This is DB. This is B. Multiplying, we get this one, and these are the degrees of freedom, 1 to 5. This is for element 1. Do the same thing for element 2. Element 2, these are betas and gammas. This is TAB transpose DB. This is for element 2. Degrees of freedom, 1, 5, 4. Do the same thing for element 3. These are betas and gammas. These are coordinates of these nodes. So this is K sub C for element 3, 4, 5, 3. And for element 4, K, for element 4, it is different in one sense. You see, for elements 1, 2, and 3, we didn't have convection taking place from any side. But for this one, we have this one. For element 4, we have convection taking place here. For element 4, these are betas and gammas. K sub C is this. But there is another H component to this here because there is convection taking place here. And if convection is taking place from side IJ, remember we solved this problem here. When there is convection taking place from this side, we found this. We need to apply it, HTL over 6. This one for that element 4. So apply it to element 4. This is this one. This is T infinity over times L over 6. This is this one. Multiplying, we get K sub H to be this one. Again, degrees of freedom 235. This is K sub C for element 4. This is K sub H for element 4. Add these two, we get this one. 12.5, let's check 12.5 plus this one, it would be 25.8. Yes, this is this one. So add them together, we get this one. This is K sub C, this is K sub H. Time to create we need still force vector. This is our global stiffness vector. This is our global heat conduction matrix, putting them together. Now, heat flow vector, for elements 1, 2, and 3, it is 0. There is no, for this element 1, 2, and 3, there is no heat source, there is no conduction taking place from this side, there is no convection taking place from any side. So it is 0 for this, except this one. For this element, convection is taking place here. So for this element 4, we have this convection taking place. Is alongside IJ. Let me quickly show you. This was this one actually. This F sub. We don't. This is F. We are looking at this one. There is no this term. There is no term here. This one for element 4 there is convection, and we said that for this one replace Q here with HT infinity for side IJ. So we use this one, 110, but replace Q with this HT infinity. This would take care of element 4. For element 4, that would be this one. Plug the values, we get this one. The system of equations now would be this. We have 5 nodes. How many degree of freedom per node? This is a 2-dimensional heat transfer problem. We have five nodes. 1 degree of freedom per node, that's just temperature. So again, our global stiffness matrix will be 5 by 5. That is this one, 5 by 5. These are temperature, this is temperature vector. Now, right-hand side, they need to apply the boundary condition. This is 1,000 and 1,000, this is what this thing's coming here. But node 1 and 4, you see here, node 1 and 4, this node 1 and 4, temperature is fixed. For these 2 nodes, temperature is fixed. So we have to correct for nodes 1 and 4, we have to correct the system of equations so that it gives T1 to be 100 and T4 is 100. That's what we have, this one, F1 and F4. This equation, we have to correct it so that it gives T1 100. To do this one, make this one 0 here, that's what you see. And this one, make it 1. So, and then this one, F1 would be 100. So if you multiply this row by this column, you get 100. That's what we wanted. Do the same thing for this one also. Make this one 1 and make this one 0, like what you see here. This is 100. This is the system of equations ready to be handed over to Nastran for solution. And the result of this is this one. T1, of course, was 100. This is 69 and 69, and then T5 84, and that's it. This is the temperature distribution, and this is the end of this document actually. All right, any questions about this problem? Any questions? How did you get the negative 5,000? Well, that's a, here, one question is, how did I get 5,000 here? It's of course not negative 5,000. You see, one step here is, so this is what we covered this one, but now what happened to this? Let me explain where it is coming from. You see, look at this last row, compare it to this one. You see this term was changed to 0. This is the same as this, this is the same as this. This one was changed to 0, and this is the same. So where is it coming from? Well, the point is that when, let's go back one step. Remember when we made this one 100, so I have to make this one 0 and make this one 1. But when you make this one 0, if it is 0, it's not symmetric anymore. This, remember, this global stiffness matrix is symmetric, and symmetry plays an important role actually in reducing the number of computations and make it faster and more efficient. But if you make this one 0, like what we did here, and not do anything here, then it's not symmetric anymore. Then the matrix will be very sparse. Computations are really, you use a lot of time, energy, computer wastes a lot of time for just doing something which is really not needed for this sparse matrix. So we like to keep it symmetric. To keep symmetry, we make this one also 0. But we can't do it without anything. To make sure, to be able to make this one 0, we have to multiply negative 25 by T1. But T1 is 100. T1 is 100 from the boundary condition we did it. So negative 25 times 100 is negative 2,500. So this is one item. This is the same as this one. Now this one, we made this one 0. But we can't just, if we do it like this, it is not symmetric anymore. If we make it 0, we have to make this one 0, like what we did here. So in order to keep symmetry, we like to make this one 0. In order to make it 0, this one was to be multiplied by T4, which is 100. So negative 25 times 100, it is negative 2,500. So negative 2,500 coming from here, negative 2,500 coming from here makes it negative 5,000. Take it to the other side, it makes it 5,000. So in order to keep symmetry, we made this one 0 and this one 0, but we cannot just go and make this item 0 without consequences. We have to make up for this. That 5,000 makes up for these changes that we made to this and this. In other words, negative 2,500 times T1 and negative 2,500 times T4, that makes this 5,000. And in doing so, we preserve symmetry. Computers are now happier. They do these computations faster, and it is what we want. We prevent these sparse matrices, which are time-consuming, waste of time for computers, especially those very large problems. It is important to preserve symmetry. That's what this 5,000 is coming from. All right. Any other questions, anyone? Any questions? No questions. So what Today we did two-dimensional heat transfer problems. This is what our discussion was, and also we did this when we have heat transfer convection from the tip of the last element. We solved several problems here. This is the end of our discussions. One more item, let me just remind you, for the final project, it is, I'm sorry, for the final exam, it is next Monday. You go to Canvas at 10 o'clock and take the test. You don't need to come to Zoom, just directly go to Canvas and take the test. 10 questions, 2 points each, and another 2 questions, 4 points each. So makes up overall, it is 28 points. It's for 1 hour. You take it at 10 o'clock and you finish at 11 o'clock. The test is designed for 1 hour. So you are done at 11 o'clock. Make sure that your internet, your connection, your electricity, everything works fine, because I cannot do anything if you have problems. If you are not sure, you can go and take the test on campus. It's more reliable. Make sure that you are able to take this. This is your responsibility. It is accumulative, it covers everything. And it is like similar to what we had for our previous quiz last week. So 10 questions, 2 points each, and another 2 questions, 4 points each. That is our final exam. After that, you are done. We finished everything that we wanted to cover. Again, it's next week. Final project for the activity. The project report is due this Wednesday by 12 noon, no later than that. But don't leave it for the last minute. Go ahead and do it today or tomorrow. It is open, Canvas is open, and you can upload your solution, your report. All right, with this, that's all I wanted to discuss. Any questions, anybody, anything?
Hey, Professor, if you're done with this class, can I ask you a question about the final project?
If you, yes, you can ask the question. Of course, during my office hours, you can always come and see me also. But if it is a short question, I can discuss this. You want to discuss with me or right now in the class? You want to?
I'm fine to discuss in the class.
Yeah, tell me, what is the question?
With regard to plotting the cross-section of BB, the cross-section BB, that needs to be like data taken from the elements and then plotted with respect to position, correct?
Right.
Okay.
That's right. You take these stresses from, you take sigma x from phi map, take these stresses with their coordinates, with their locations, and put them in Excel and plot them. Show the profile of variation of sigma x along section BB. But take these stresses from phi map and then use Excel to plot.
Does PHMAP have a feature that relates the location of the element to that?
The coordinates, it gives you the coordinates. That F065 file, it gives everything.
Okay.
In that F065 file, it has all the information.
Gotcha. Thank you.
All right, sure. All right, anything else? Anyone? All right, with this, I stop here, everyone. This is the Thanksgiving week, so enjoy the Thanksgiving also. And this was the last class meeting. Take care, everyone, and good luck with your final exams. Take care, everyone. Bye.
Thank you, Professor.
Sure.
Thank you, Professor.
Sure.